Alright, so now we're going to look at how to do a worked example of a molar heat of combustion calculation. We're going to use some experimental data which will lead to some interesting results at the end. Alright, so here is our question, and it's very, very simple. Basically, a student here has about 100 mils of water, which they've heated from 20 to 75 degrees. Notice that there are the point zeros on there. That's really important. That helps us with our significant figures. Of ethanol, she started with 43.56 grams of ethanol and ended with 41.36 grams of ethanol. Now the water was heated to heated in a 30-gram aluminium can, or aluminum, and it has a heat capacity. Aluminium has a heat capacity of 0.90. You can add an extra zero on that. We use the experimental data here to calculate the experimental value for the molar heat of combustion. Cool. So there are several steps we want to do. The first thing we need to do when we're doing a question like this is we want to plan your equations. So you quickly write down all the equations you need. This equation here is wrong, and I fix that a little bit, but that should be an N. Alright, now, so we've got the delta H of combustion is delta H overall, or total. We'll see that in a second. Total divided by the moles of the fuel burned. The delta H is very simply MCAT plus MCAT. So mass of the water, specific heat of the capacity of the water, and the delta T, which is the experimental data we collect. Then the mass of the aluminium can, the specific heat capacity of the aluminium can, and the delta T, which again is the temperature we collect. So those are the equations we need, as well as the very, very simple, up the top here we go, moles equals mass over formula mass. Alright, so the second step, write down your unknowns. Okay, so for this delta H1 here, we don't know delta H, that's unknown, but we do know our mass of water is 100 grams, 1 ml of water equals 1 gram. It is 4.18 specific heat capacity, mass of the can is 30.0 grams, and it's got a specific heat capacity of 0.900. We also don't know the amount of the moles of ethanol. What we do know is the mass of ethanol, which ends up being about 2.20, and we know the formula mass of ethanol, which is 46.01 moles per gram. So then we need to work out our unknowns. That's our next step. That's our final step, but there's a few in between here. Okay, so delta H total. It's quite simple. We plug in all of our equations, all of our numbers into the equation. So that's 100 grams times 4.18 times 50, brackets, and minus 100 grams, plus, brackets, minus 30 grams, because it's the minus MCAT, times 0.9, times 50 degrees Celsius. Again, you'll notice that that number there actually comes from both. That's the number on this thermometer right here. And that gives us minus 20,900 plus minus 1,350 joules. Okay, so that's the enthalpy change complete. Now, we want to work out how much of this per mole, so we know how many moles we used. So we've got 2.2 divided by 46.01 gives us 4.782 times 10 to the minus 2 moles. Nice. Pretty straightforward. Now we finish this off. Really simple. So we go this number here, which is the delta H total, divided by the moles of fuel, which is that number there. And that gives us this stupidly big number of minus 465,328.4 joules per mole. That is too big. That is nonsense. We don't want that. So we put it into kilojoules, just to make life easier. And it is 465.3 kilojoules per mole. And that's specific heat capacity. Now what you will notice, and this is one thing for another time, is that that number is extremely low. The accepted value of for delta H of combustion for ethanol, the theoretical value is 1,300 or minus 1,360 kilojoules per mole. So it's a disturbingly low number, and you're going to need to work out why. But that's for another time. See you next time.